Now it's good. Yes, you please continue. Sorry to distract you.
Okay, yeah. Yeah, my name is Sonny Bailey. I'm doing a research associate role in iceberg detection. I'm here in Tromsø supporting the global ice services in understanding artificial intelligence techniques and technologies for the use of iceberg forecasting and monitoring. So yeah, a little bit of background context. So with climate change lowering the quantity of ice present, decreasing of sea ice levels is having an increase in iceberg production. So as the amount of sea ice decreases, there's then more space for icebergs to break off of glacier tongues and ice shelves. These then drift into the shipping lanes in Atlantic Ocean and Arctic Ocean and in the Antarctic. Every year, there are still around 2 to 3 iceberg incidents, despite the modern progress that we've made on technology on board the ships and in terms of satellite radar, synthetic aperture radar. And the goal for this presentation is the key takeaway that I want people to take away from is that better iceberg detection is going to mean earlier warnings, a safer navigation, and reduced accident risk. In fact, in 2007, the ship picture you can see on the right is one of the most recent um, iceberg collisions or ship incidents. And so, yeah, this is still an ongoing problem, and it's projected to still be an ongoing problem because of climate change. So that is some background context. A little bit of introduction to what icebergs are. They are pieces of freshwater ice broken from a glacier tongue. Glacier tongues are usually found in the Arctic, and therefore the iceberg shape is likely to be not flat on top, so more irregular, more sharp, angular shape. In the Antarctic, they break off more ice shelves, so they are larger and tabular. In fact, some of the largest icebergs in the world break off of Antarctica. And they can drift into open water, which is where they can become hazards to ships in places like Newfoundland, or they can become embedded within fast sea ice flows, especially in places like Svalbard, Greenland, and the Northwest Passage. So as they say, they are classified by both size and shape, and these can be based on the in situ observations that you find on ships and also from satellite imagery. It has been an important field since the importance has been raised due to the sinking of the Titanic. Everyone should know that 11% of an iceberg is visible above the ocean surface, and that makes it essential for remote sensing and advanced detection methods. And the website there on the bottom right just is a little play around that you can use to draw your own icebergs. You just draw an iceberg, and it will ensure that only 11% show above the surface. So icebergs topple over to as well, which makes it more important for monitoring. So the idea I'm going to talk about actually came from wanting to apply a machine learning algorithm that we had developed in our department for astrophysics problems. We were using it to find the most massive objects in the universe, so galaxy clusters. But this has nothing to do with the work I'm giving you. This is just like where the model that I'm going to present was used last. So here we got to focus on Franz Josef Land, which is a very active region for fast sea ice. And fast sea ice is basically sea ice that is connected to the coast, whereas you have pack sea ice, which is not connected to the coast, or drift ice that is not connected to the coast. But icebergs that embed within fast sea ice are easier to monitor because they do not drift as easily. So what we are looking at here, and the red square on the left is a SAR image acquisition. And the little green squares that you can see are the Sentinel-2 optical imagery. We have to use both Sentinel-1 and Sentinel-2 for validation purposes. And a little bit more detail here. So we have a geo-referenced Sentinel-2 dataset on the left there. and you can see the fast ice, and you can see the sea ice as well. And on the right there, we have a SAR image, Sentinel-1, ground range detected Sentinel-1 SAR image. And it shows the same area as the Sentinel-2. And then finally on the right, we have the landmask image, and we have to have a landmask image because we have to mask out land features so that a deep learning model does not learn these features. So the deep learning model is better able to understand the features of icebergs and the surrounding background. So what is the problem that we are trying to solve? We cannot easily separate icebergs from the sea ice in the literature due to similar backscatter signatures created by SAR. So if you think about it, icebergs have a very bright or a dark signature in SAR imagery, depending on multiple factors. But so too do things like hummocks that you find in sea ice flows. This creates uncertainty for operational ice charting, and it can also create problems for manually visualizing icebergs in the imagery. So we need a way to try to solve this problem. And the way that we have tried is we use something called a dual polarization intensity ratio anomaly detector. And all this is a contrast enhancement algorithm. And we take what we take is we take a cross-polarized image, VH, and then we take a co-polarized image, VV, and we basically create spatial averages. These two boxcar filters are spatially averaged over each other. What that does is create a blurring effect on the image, and so to be able to gain back the information about the intensity, we can multiply by the cross-polarized HV image, and that you can then represent as a threshold, and this basically gives you a contrast enhancement between the icebergs and the surrounding background. We can only do this really for dual pole Sentinel-1, but you can also do it for full pole as well. But in here we do it for dual pole. So traditionally, a lot of iceberg detection algorithms, we use something called constant false alarm rate methods to find the most optimal performance. And the picture on the left there show a rock curve, a receiver operating characteristic curve that you create from finding a single threshold, which require a lot of statistical tuning of the SAR data of the. But for real world detection, we want a more automated process with lots of data that we can do in a shorter amount of time. And that is where the deep learning can come in, because we can use these methods to help ice services automatically distinguish icebergs in the SAR imagery. Deep learning has shown promise in other areas as well, as I've shown with the Astro example. But my project is now expanding upon this using a YOLOv8 fast, efficient object detection model. Object detection is basically you draw a bounding box around what you think is the iceberg, but you also draw it around the background too, so that the machine knows that it is not just the iceberg to look for, but also is it in the sea ice or is it in the open water? So this is the methodology that we use. We acquire the data, we radiometrically calibrate, we create the covariance matrix, and we boxcar filter out any speckle. And from there, then we can create the images from using the Python code, and you can then label these images. And it's important to label the iceberg images manually so that we then train and evaluate the model to see if it knows where are the icebergs or not. And then after that, you can do a test data set on unseen data. So we use a different SAR image for that. And to increase the size of the data set, we can use data augmentation. We basically flip the image 3 times, and this gives us a bit more data to work with. The reason we do that is because one of the limitations of deep learning, especially for iceberg detection, is we do not have a large amount of training data. We are still trying to work on that, but a manually labeled iceberg data set is very, very difficult to produce from a manual standpoint. but in the future, this is projected to also improve. So yeah, the next step is optimizing this model for iceberg detection. And this requires a lot of training and a lot of fine tuning, hyperparameter tuning. So here's what it looks like. So the top two images there are basically the input HH and HV SAR images from Sentinel-1. And we apply the detection algorithm that you see, and we get basically these images on the bottom. So you can see the icebergs clearly in this first image, and then the optical image is more for the validation aspect. So here's how we're doing this. Because of a high computational load, we don't want to process the entire SAR image at once because it would crash. And so we split it into subsets, which is what this animations show. We actually split into image slices. So we have 400 image slices, but not every single image slice is going to have icebergs within them. So we only label the icebergs that we see in image slice, and we get rid of the other image slices that we don't want. This ensures a very efficient process. It's a pre-filtering technique that is important to create the input data for the model, which looks like this. So on the top there, you see the Sentinel-2 imagery, which we don't feed into the model. We just use for the visual manual identification. But we do feed the bottom images into the model because that is where you draw the bounding boxes around what you think are icebergs. And you draw them around the very bright dots, but also anything that you see in both the optical and the SAR. So when we're labeling, we never do it for just one ice. If we see one iceberg in one image, but not in the other, we do not label. We only label if we see in both images. So that is a limitation there as well because of incidence angle, things like weather, noise floor, lots of different factors can come into play. Okay, examples of predictions that have been made by the models. So what we see here are the images that show the test outputs with a confidence score. So on the bottom there, we see an iceberg that is 70%, that the model thinks is 70% is there, basically. And that is very useful then to give to ice services and ships because we can translate that into a coordinate, latitude, longitude report. And so that is the purpose of the testing. We then quantify this test as well. We can quantify the performance for the training and the validation using precision and recall and F1 score. The main goal in the graph there is we want to try to stay on the top right as possible. So we try to get as far to the top right as we can. This basically, each point on a graph is going to represent a threshold of how confident the model thinks is an iceberg. So here are the training results, and the loss curves there show very well that the model is learning these features. And we have about a precision recall of around 0.8. And this basically means the model correctly detects about 8 out of 10 icebergs in the test images. With minimal false alarms, which could slow decision making if there were too many false alarms. So this means the model is automatically good at flagging imagery. Like the size of the iceberg, because any iceberg below 100 meters for the spatial resolution that we use of 90 meters is going to be a lot more difficult to detect. So there is a limitation again with the size of the iceberg. But the whole thing, what this means for ice services and mariners and for people in the AI atmosphere as well, is that there's faster iceberg identification, improved detection reliability, enhanced safety in the sea, and there is good operational potential. We are ready for trying to test this in a live context as well. So to conclude, YOLOv8 is a good object detector that shows very strong potential for good operational iceberg detection in Franz Josef Land. We have yet to test it in open waters and different environments, but that is in future work. This can directly support the safe navigation and for more efficient ice charting. So the next step is real world testing now in collaboration with ICE services, other researchers, other people who are interested. So we're looking to partner with these people and to try to test this approach. So that is it. And I appreciate everybody listening. We'll take any questions.
Excellent. Thank you very much, Sonny, for a very nice presentation. So any questions from the audience? Maybe I start, Sonny. Sonny was my former PhD student. So basically, he started with CFAR-based detection algorithms, but he has improved it using YOLO now. But still, you use the dipole ratio detector. So my question for you is that this is just the case for Sentinel-1 images because that detector is for dual pool data, or you have adopted for quad pool data as well?
So for this work so far, we have only used dual pole Sentinel-1 data with the dual anomaly detector. But in the second part of my PhD, which we were doing detection comparison, we did use the ID PolRad detector for quad pole data for ALOS2 SAR data, but we didn't really use it here for
Very good.
this purpose due to
Very good.
coverage. Yeah.
Yeah. Any questions? Or I continue?
Sorry. Thank you,
Yes, Hisham,
John,
yes, please.
Johnson, for your presentation. It's very, very interesting. So I would ask if YOLO, this algorithm, it's good for using for landslide. In my case, I can use it.
Yeah, YOLOv8 is an object detector that is good for versatile applications. The thing to think about with YOLO is that it just does one forward pass. I don't know if he has talked about backpropagation and your gradient descent. But for YOLOv8, we only do one forward pass rather than do it in a regional proposal area, which would be for faster RCNN and other deep learning models. So YOLOv8 would be a good one for any task that just you require a bounding box, or you can do instance segmentation with YOLOv8 as well, where you draw the polygon, the shape of the landslide, and the model will then learn the shapes and features of the landslide. So you can certainly do that, but I would recommend instance segmentation for landslides specifically. Whereas for icebergs, all we have to do is draw the bounding box around the image because all that is all the operation cares about. Yeah.
Okay, thank you. Thank you.
My question for you is that iceberg ground truthing is one of the main challenges because it's different than any other applications, especially in the Arctic areas that you are not accessing to icebergs in the field. And if you're gonna draw it manually, how do you trust that you do it properly? Maybe you are mislabeling it with something else. Maybe there are some small ships there or some other targets that look very similar to icebergs. That's the first question. And second question is that because I think this is time-consuming job. How many samples did you manually label? Is it enough for YOLO algorithm? You think that even with that type of job that you do for ground truthing, does it worse if you're gonna do transfer learning or scale up for operational services?
Yeah, these are both very good questions. And so for the first question, this is the reason we use the land mask, because we have to get rid of any land features to first of all. So the process of manual labeling is to first do a process of elimination. What is it that we do not want there in the images? We have to understand that land mask is good for getting rid of anything on the land so that we are only focusing on the coast and in the sea. And then after that, we have to think about other objects in the sea. We know that a ship is an elongation in a SAR image to have two lines coming out at each end. So we are now trying to we have the expertise of understanding different features of objects such as ships and buoys and other things like oil spills. that you may find in the images, and we do not want to label those. But the key thing for icebergs specifically is we can look for in the optical image. We look for the shape of the iceberg, but we can also see a darker area of the iceberg, like the shadow of the iceberg. So if we see the shadow on the iceberg, then we know that it's more likely to be a much higher up than the surrounding ice. So it could be an iceberg that we can then label. And for the second question,
how many samples did you collect?
Yeah,
how many samples did you get as a label?
About 4,000. About 4,000. It was a tedious process. The labeling process is time consuming. It's the most laborious part of the work, but it's also the most important part of the work because you need as many samples as possible for the model to have a very good representation of the data. So we did the data. We did about 1,000 or 2,000 icebergs manually, and then we data augmented around that to try and get it up to about 4,000 in total. So, but I think that is fine because then the model is learning the iceberg shapes from different angles with the data augmentation, which is what it's good for. But there is still room for improvement. We're trying to get more manual label data sets. It's going to take a lot of time. And there's only so much we can do for areas that have only small amounts of coverage for images because in the Arctic, yes, there are Sentinel-1 and Sentinel-2 images, but they may only be found during the times where there are no where you can get polar nights and polar days, because cloud cover is a problem for Sentinel-2. So it's difficult to find the good days and good dates. You have to think about all of this.
Okay, very good. Thank you very much. Any questions?
I have a question, please.
Yes, Sahar.
First of all, thank you for your presentation. It was very nice because my father is a ship captain. I think that this would come in handy for navigation. So you mentioned that you use Sentinel-2 for validation. Which part did you use the validation with Sentinel-2?
Which type of Sentinel-2?
Which part of the operation did you use Sentinel-2 to validate?
So we only used it for the labeling, and we do not include Sentinel-2 in the actual model training or testing because of the differences in the resolution.
I wanted to make sure that because of the different resolution in the both data of Sentinel-1 and Sentinel-2, and also I think that it is hard to find a time that both data are operating at the same time with minimum gap in the acquisition time.
Yeah. So although we do talk about the spatial resolution, what I didn't mention is that we do when we put the images into Snap and into Python, the goal actually for the Sentinel-1 image is to match the resolution of the Sentinel-2. We do that by changing the pixel spacing in Snap, and then we georeference and we clip to the specific Sentinel-2 image so that we only have that one Sentinel-1 image, and then we do the image slicing. So that is how we use the Sentinel-2 for Sentinel-1. And yeah, for ship captains, we actually noticed at the meeting that there are some shipping and ice services that are still a little bit more reluctant to apply the AI, but they are probably looking into doing it within a 5 or 10 year time frame. And there are some people that still prefer traditional ice charts and still prefer the traditional. So it is good to hear about shipping aspect too.
Thank you very much.
Thank you. I have another question. You spoke that you just label the icebergs that are kind of stationary and seen in 2 images. not if they don't if they have moved, you don't consider them labeled to use for training, right? Did I understand correctly?
Yes. So as long as we see both icebergs in the optical and the SAR, even if the iceberg is only a little different from the location in the SAR, but it's still there, you can kind of deduct that it has moved just a little bit because of the time difference. We still label them because they're both there. If there is no iceberg there and there is an iceberg in the SAR image, or if there is an iceberg in the optical but not in the SAR image, then we do not try to label.
Maybe if there are icebergs within just like Kansfjord and Fjord, which they move very quickly, maybe it's now there in one scene, but in the second scene it has moved somewhere else. You don't label them, or do you? Because your main focus has been iceberg in sea ice or icebergs in open water as well.
Main focus has been in sea ice for now.
Only sea ice. Because okay, yeah,
for
if they are in sea ice, they look like more stationary. They don't move much because it's also, frozen within sea ice. Yeah, it works. It makes sense to me that you have focused only on those icebergs within
Yeah.
sea ice. Yeah,
Yeah, in fast ice because
that's
connected
nice.
to the land, and the icebergs will become grounded and they will not move as easily. In open water, we expect there will be a lot more movement, especially for where the International Ice Patrol in the United States, they just offered me a collaboration for the future to get open water labeled iceberg data. So they want to label all the data set for me, and then I train the models for them. But in open water there will be a lot of movement and lots of drift. You have to have a validation data that is more or less at the same time for that reason. But in sea ice it's a little easier because we know it is there.
Very good. I think one comment I would like to have. Bipin is also with me. Bipin is a KTP associate. He has also worked with detection task using deep learning algorithms like YOLO or others. But we have found that YOLO, which was developed by Ultralix, is kind of commercial package, and you might think about other detection algorithms if you're gonna scale up or use it commercially, or maybe I don't know if those organizations can use it like for free. This is also one concern I think I have.
Yeah, Ultralytics, they have a free, I mean, I use the free version for research, but in a commercial setting, yeah, you have to pay. You have to pay Ultralytics for use of YOLO, which I don't really get that why, because it's a deep learning technique and a method that you can easily make with Python code. I just don't think that it is necessary to pay for the CNNs, because again, for research purposes, it is totally free of charge. So people will exploit it for that purpose.
Yeah, very good. Any other questions? Maybe one more question. Did you do sensitivity analysis with respect to iceberg size? So can you give me an insight? What is the limitations with detection of the icebergs in Sentinel-1? So how big iceberg can you detect?
Yeah, this is a good question. We didn't do a sensitivity analysis per se, but in a discussion for the paper that I wrote, we talked about the resolution limits, because the Sentinel-1 ground range detected for that area in Franz Josef Land, the spatial resolution is 90 meters. And so my thinking for that, which I spoke to Armando about as well, is that anything below 100 meters length will not be detected by the Sentinel-1, and that is the technical limitation, again, the size of an iceberg. So anything above 110, 120, more likely to spot in a SAR image. Even if we do find icebergs that are smaller, but it will be difficult to say if they are icebergs or not. It's because, again, the 90-meter spatial resolution is only for Sentinel-1. The validation data is usually a bit of a better resolution. So that, again, we can use that for some we try to cross-reference, but it is it is very good for right now. We don't have a lot. We don't have the progress with resolution limits and swap widths and stuff like that. So it's going to be, we have to wait for Roselle in 2028 and of potential. I think Sentinel-1. I can't remember. There's another Sentinel-1 due to launch later this year, and for the polar regions as well. I'm trying to. They spoke about it, and I can't remember the technical details, but yeah, the resolution 90 meters. Anything below 100, 110 is difficult.
Okay, very good. So the labels that you have got, the minimum resolution, not the minimum size of iceberg could be like covering 2-3 pixels, right? This is what you say, right? The labels that you have got, at least you have got 2-3 pixels for your iceberg labels.
Something around, yeah, about 2 to 3 pixels. Anything. We do sometimes find bigger ones, but yeah, 2 to 3. I think is the normal in the Franz Josef Land.
Yeah, very good. Any other questions? Okay, very good. I just stop sharing here. Thank you very much, Sonny, for very excellent presentations. I appreciate it. So we continue with the meeting after this. Thank you.
Thank you.
I just stop recording. Stop.